Yeah. Today we'll be going to start Hadoop. Okay. So Hadoop is a big data component. I think you all have heard of this thing. It's a bit, actually what we have learned till now on top of data engineering. SQL, we have learned some basic, what is business intelligence parts and why we require business intelligence and why data engineers are required over here. Those kind of stuff we learned. We learned Python to integrate the different external data as well. And after that, we have learned some more things on top of cloud. What is the cloud concept? How the cloud should be working? As a data engineer, if someday we require to install a particular database or anything, so that thing we can also support by using clouds and all. We have the basic knowledge on top of cloud, but although we do not have any hands-on till now, but yeah, somebody. Nikhila, can you please go on mute? Yeah, thanks. So, yeah, so what you're telling? Yeah, we have learned cloud computing as well. It's very basic thing. What is cloud? We can actually now spin up a server from AWS side or maybe from Azure side. There's no such issue, but for a database spin up, it's not very much tough. Whatever we have done for MySQL server, we can just directly search for that thing and we can quickly launch an RDS. RDS is, just that particular software we can quickly launch it or spin up over there. So uh, we learned a lot on top of this MySQL and all. So today I'll be starting Hadoop. It's a big data component. Actually, in our real case scenario for a particular systems, more of the system they are having millions, more than millions. Billions of records are there per hours or maybe per hours it's fine, per day. So we are loading the data from source system to target. That means the ETL tool is doing that stuff. But the conventional ETL tool, they're taking much more time. They are having each of the ETL tools should be having their throughput. Throughput means number of rows per second. They will be transferring or they'll be cleansing, transforming per second unit, just like a mileage. Yet throughput is the measurement of a efficiency of a ETL tool. Okay, so how it's getting transferred with various transformation with various business logic from our source system to target database. So the conventional ETL tool, it's taking much more time to load the thing, which is not acceptable because we have very much critical data. Suppose we have billions of records that needs to be refreshed within hour, but it is taking more than hour. So people are not getting it without in time. Okay, so there we have the big data technology to solve the big data solution. We have large data set, then we have the thing in mind that that thing can be distributed in nature in multiple computing engines. Okay, and the computing engines, they will be analyze the data based on their portion, the task node, and after that when everything is been completed, then they can submit the result to the master node and master node can get the output. So this is the overall concept. Actually we also should be having that knowledge with us. But actually in the Hadoop, what a Hadoop developer can do, actually that is the concept. The architecture is already there, the name node, task node, those kind of stuffs are already there. Just we need to have some developing. We have to develop the code on top of Hadoop so that we can distribute the thing properly. Actually, distribution the thing is also not required by us. So it's the internal architecture of Hadoop. I'll be just going through what is the architecture of Hadoop. But most of the thing can be handled. If there is a node failure, Hadoop can automatically take over. Hadoop has that capability that another node can take over this node's data or this node's calculation or anything. What is the failure node? So Hadoop has everything. From the developer perspective, there is very less to develop to handle those kind of core nodes. Okay, just like for Python, for Java, whatever we are writing the code, the same kind of code we will be writing over there on top of Hadoop. Okay, a bit different is there for the data to be distributed in nature. There is a bit, I mean, a bit different in languages part and all, but it's almost same. So whatever we have learned for Python, the data frame creation and all, it's similar, but to make it a distributed one, there is some changes. The coding part we'll be learning tomorrow. So today we'll be just learning what is Hadoop and especially its architecture. Okay. So I mean, the system itself, it's a fault tolerant as well as with the calculative perspective, I mean calculation perspective, it's very much efficient by itself. The developer just do some top level codes on top of that one, just like joining the thing, aggregation of the things, whatever we have done on by the data frame itself, the same thing we can do. I mean, the data frame can be worked over here as well. I'll be just giving a basic introduction on top of that one today, and tomorrow some coding concept on top of Hadoop, how that can be possible, that we can cover. Okay. Okay, let me just maximize the screen. Okay, so Hadoop is an open source platform. We can install it at our systems as well. But I mean, there are, I mean, for Hadoop, there is Horton. I mean, there are lots of vendors are, I mean, Hadoop is controlled by actually one product owner, but the software, the distributed file systems and all can be provided by multiple softwares or multiple IDs can also support on top of that one. We can definitely discuss on that topic quickly. So it worked on top of distributed storage. So distributed storage means Hadoop will be working. I mean, as I told that we have to distribute the data. Distribute the data in where? In storage. Okay. So the storage system where we are keeping the data or we are calculating the data, it's distributed in nature. Everything is not, every computing engine, I mean, only one computing engine is not calculating everything over there. There are various computing engine and those are distributed in nature as well. That is called distributed processing. So the storage system where we are storing the large file that can be distributed in small files and can be stored in distributed in nature. Even for the distributed computing power is being used over here. For each of the storage system, a computing machine should be there to compute those stuffs. Okay. If you could remember at the end of yesterday's session in AWS, there is a component called EMR. Okay. So EMR, Elastic Map Reduce. So that is also worked on top of Hadoop. Okay. It's a big data component at AWS side. So we have Databricks over there in Azure. It is having the similar kind of stuff. But in the backend, how Hadoop works and all, in EMR also it's working on top of Hadoop. So we need to know what is Hadoop, especially that last two things. We in Hadoop we have distributed storage and distributed processing. This is the main thing of Hadoop. So if we just go ahead with the main thing, I mean the main architecture point of view, what is Hadoop? Over here, the three things, MapReduce, Yarn, and HDFS, these three things are the core part of Hadoop. And apart from that, whatever you are seeing over there, those are add-on services which should be working on top of Hadoop. Those are not mandatory. Okay, I can use Pig on top of MapReduce or Hive on top of Hadoop. I cannot use Sage, Mesos, Spark. That is required or not required. That doesn't matter. But Hadoop should be coming with these three components. HDFS. HDFS is for the distributed file system. Okay, so if we have large data set, we are splitting those things into small chunk of files and we are storing the data in HDFS. Okay, Yarn, I'll be coming all these three core components quickly. Yarn is, a resource allocator. Actually, on top of HDFS, it's working. HDFS means distributed file system. I mean, in each of the file to control those files, small chunk of files, we have to keep allocate the resource. Resource mean compute engine. Okay, means a particular server. We need to allocate this thing, and that is called uh, yet another resource negotiator. This is the full form of yarn. As for the naming convention, I think you can understand how it works. The resource means the compute engine, means EC2 server, I can also say. Just like in EMR clusters, there may be various EC2 server. Okay, so that can be controlling the particular HDFS system, and this yarn will be controlling that EC2 servers, which EC2 server which controlling which HDFS file system. Okay, and on top of that, a bit advanced thing, that is map reduce. So this is the main thing, which operation should be mapped and which operation should reduce the data. The concept will be working on top of yarn. Map reduce will order the thing to yarn. Yarn will be allocating resource on top of different file sources or file systems over here. So this is the main thing. Apart from that, whatever add-on services are there, they're just integrated on top of Hadoop. Suppose we have Hive. Hive is a query engine. Okay. On top of MapReduce, whatever data has been, we have whatever data on top of HDFS itself, we can call the data by a query engine called Hive. Just like I told you yesterday, that on top of S3 bucket, okay, on top of S3 bucket, we can just do create table name, and we can point a particular directory over there, putting some more parameters. What should be the header? What is the file format and all? Then a table should be created on top of particular file. Okay. So this is the important stuffs. Hive is a query engine. This is Pig is also the same thing, but a bit different for each of the services. Just like as per the architecture as well. If we use Tej, then we are not using map reduce. For Hadoops, we are not using map reduce over here. In Tej, it's already have a map reduce component within it. That's why the hierarchical architecture is very much meaningful over here. If you use Mesos and Spark as well, it's working on top of HDFS. So from Hadoop core system, it's only taking HDFS. It's not using yarn and MapReduce. It should be having its own MapReduce and yarn system within Spark. Spark is, one of the most important steps in today's big data calculation. It's a most important, I can say, uh, the valuable one or most suitable component or add-on services, which is nowadays, which is most popular one on top of Hadoop, it should be working. So from Hadoop, I'm not using, if I'm using Spark, I'm not using MapReduce and Yarn. I'm just only only working on top of HDFS. Only I'm taking the lower component, and then Spark can work on top of that. Okay. But if I am using Hive, I have to work on top of MapReduce. If I'm using Pig, it should be on top of MapReduce. There is something more over here. Oozie. Oozie is a job scheduler. Okay. So whatever job we have designed over here, Oozie can schedule those jobs. So this kind of stuffs are already there. Lots of things are there. Apache Ambari, it's the user interface where we can check the resources are getting allocated properly or not, the sizes of each of the resources, means computing engines. Okay. So the basic admin portal from which we can control the thing, it's Apache Ambari. Zookeeper will check whether yarn is working properly, MapReduce is working properly. So this component is just for inspecting purpose. As per the screen, you can, as per the logo, you can able to understand. So the entire thing can be it's already been packaged, and it's come to us. So maybe someone says that he's a big data developer or Hadoop developer. So actually Hadoop has that capability to do everything. We just have to do, the developer just have to do a bit of codes, maybe in Python. Maybe someday, you can learn that someone is working on PySpark. PySpark is nothing but Python language used on top of Spark. Spark technology. Okay. So whatever Python code we have learned over there, we can write the same thing in Spark. A bit difficulties or a bit different things should be there, which will be helping us the map reducing part. That means the distributing of data while calculating the thing. Okay. So that much difference we can learn tomorrow in tomorrow's session. I will be, arranging some code snippets, or if there is anything I can able to show you. Okay. So this is about the overall architecture. How it's working and all, and how the big thing is. How what everything has been controlled over here. Okay. The big data part. Any doubt from anyone? I'll be just going ahead to the next slide. Okay, Akhil, you want to say something? Okay, I think no. Fine. Okay, so just I mentioned that there are lots of, the component is having, some of them is having some query engines operation only. Just like Hue, Presto, Phoenix, Apache Drill. Those are not mentioned everything over here. But those query engine, maybe in Pig or Hive. In Hive, we can use Hue to have this query engine. Query engine means it's SQL query only. So data is getting stored over there, but we have the SQL facility that I can create the SQL queries on top of their data, and the data can be easily fetched. Okay, so it's just working like a database over there, but not exactly the database. But the user interface, the data can be manipulated. Whatever the data is stored over there, I can manipulate the data by those query engine. Okay, suppose I have this. I have a particular Excel file in particular folder, or it's lots of Excel file in particular folder. I have to manipulate something. So Hadoop has that capability on this. On top of this directory, we have the query engine. I can just put a select star from this. My query, whatever data is stored over there in my directory, it can be stored as a data. Data. Columnar format over there. So I can have a quick manipulation on top of that data, or we can check the data over there. So that's why the query engine is being used over here. Okay, so and this add-on services, it's not there actually. There are some external data storage as well, which is compatible with Hadoop. So it's MySQL, Cassandra, MongoDB is NoSQL database. So those kind of data storage are also there. Those are called external data storage. For MySQL, Cassandra, we can uh, just for ETL tool, we can transfer the data from what is stored in HDFS to MySQL and external MySQL data. That's the concept by using Spark. Okay, so as the input system, we are placing the files in distributed in nature in HDFS. We can able to process the data through Spark. Okay, rather PySpark we can use, and after processing the data, we can write the data into some external data storage, and those external data storage is also been coming with, the feature is already been available with Hadoop, MySQL, Cassandra, MongoDB. Those are the databases. Okay, MongoDB is NoSQL database. That means whatever we have learned at the first day, it's not the relational database. Okay. Okay. So the topic I just mentioned some few times ago, the core of Hadoop. So the bottom portion, it's coming with HDFS. On top of that, we have Yarn, and on top of that, map. It's map reduce. So I'll be just covering a bit information how it's working one by one for each of the components. Okay, HDFS. What is HDFS? It's Hadoop Distributed File System. So what I just mentioned, it's there. It's breaking large file into blocks and distribute our storage of big data across our clusters of computers. In a cluster, there are a lot of computers. And I mean, each of the computers has its own storage devices, and it's working as a distributed file system. The storing is been divided between each of the machines. Okay. And what is yarn? It's yet another resource negotiator. It's manage the resources on top of the computer clusters. Okay, so what is HDFS architecture actually? There are several data nodes actually. Okay, and the data nodes are main responsible for storing the thing and the computing power as well. I mean, distributed computing power. Name node is controlling those stuffs. Which data should be working, or it is having the metadata information for a particular file or particular small file. It's been stored in which data node. Okay, just like a single name node can track multiple data nodes. Okay, for our HDFS architecture, we have single name node and multiple data nodes. Okay, so reading a file, if an external client want to read the file, it should come and contact with name node. Name node will transfer the particular, particular file or particular data. It can help the client node to give the information, as it's having the metadata information which data node is storing which thing. So it will transfer the same information to client node. Then client node will be searching for the same data to the particular data nodes. Okay, so this is the concept. Writing a file, the same way client node can write a file. It can take reference from name node where to write the file. It can write the file over there in data nodes, and it can just update the same thing to name node. Okay. Just one more important steps when we are writing the thing in a data node. There is a backup, or in AWS, whatever we have told, uh, itself, AWS, it's working as a region specific. The data center is keeping backup to another data center. That is not known to us, which is backup for which data center. But the same thing over here, a particular information is not stored in a single data node. That can be also circulated by one or two data nodes as well for backup purpose. Okay, so the data, maybe our information is stored in that particular data node over here. The same information can be stored in this data node as well, as per a backup purpose only. So it's that one is also having the backup of this data node. It's having its primary data as well as the backup thing as well. That why? Because this if one of the particular task node or data node goes down while doing the operation, then the another one can start working on top of that. So it's very much fault tolerant. So if you just open that Apache Ambari, I just showed you that particular architecture. It's a UI, user interface. There is a portal to open that one. A portal should be there, which is the UI, user interface. If we open that one, we can see which nodes are working. There must be some IDs. Okay. So which nodes are currently working, if there is any fault, a fault within a particular data node, and how that fault has been recovered by another data node and all. That can be measured by Apache Embed. We can check it over there. Okay. Yeah, writing of the file is completed. Yeah, backup thing I just uh, tried to mention the same thing, but backup of metadata, because this is very much important, because we have only one name node. So if the particular name node goes down, what will happen? So name node will write the data to local disk. Okay, it's local disk as well as NFS. NFS is another file storing system. It's mainly storing name nodes backup part. Okay, so data nodes are keeping backup between themselves. In the inside program, or inside, whatever the architecture and whatever programming it is having internally running for Hadoop, it's have that mechanism that data node can take backup from each one's data. But for name node, if it's only one name node is present over there in the single, if the single CPU is got, I mean, it's failed or something happened to that one, then in the Hadoop architecture, I can get the data from HDFS itself, because name node can transfer the data to the Hadoop's local system. Okay. And there is another memory that is called NFS. So it's also stored the backup information over there as well. Okay. How we can check the data of HDFS? So I told you that there is already a data, I mean, UI present that is called Apache Ambari. It's a UI user interface, just like a portal, simple portal. In the portal, we can able to see the directory, I mean, directory structure over there. Just like for S3 bucket, whatever we have seen for S3 bucket, the same thing in the portal we can see. It's storing the data in several directories. Okay, and we can, I mean, retrieve the data in over there as well. We can check the data in which directory, which file is located, and that's why, I mean, we can check the data of Apple, I mean, the particular Hadoop by this UI. And also we can check the thing from command line interface. If we're using Linux server on top of, I mean, Hadoop, then we can just open putty or just like this. And using this command line interfaces, we can check the data as well. And besides that, there are HTTP, HDFS proxies. I haven't used that thing, but I just for the information purpose, I stored this kind of thing over here. NFS gateway, that NFS I just told you over here. NFS gateway is there as well. But generally, in, I mean, most of the project we can use either Apache Ambari or command line interface to check the data of HDFS. Okay. So suppose, I mean, the entry point should be a EC2 server where we can check the Hadoop ecosystems and all. That Linux server we can open by Putty. Putty is the software to check the Linux servers, drivers and all, the drives and all. So uh, by opening that Linux server by Putty and using command line interface, we can track the thing. Okay. So those are the basic stuffs of HDFS. Now, I mean, yes, I mean, yarn, we have already mentioned what is yarn. There is no much thing actually to say over here. And top of yarn, we have map reduce. Okay. So here is a architectural diagram. What is map reduce? Let me just maximize the thing. So the big data actually it's been mapped as I told in distributed file structure. But what should be the calculation? Based on which calculation we will be transferring a particular data to a particular file location. That should be doing by this map operation. Suppose let me share something. Suppose I have an industry and I have to distribute the data, but what condition I'll be distributing the data for each of the small chunks of files? Maybe I have different. I have the industry. For the industry, there are 7 or 8 different region of this industry. Suppose I can segregate my data based on those 7 or 8 region. I can use the group by operation as like SQL, group by the region. Or just like I can partition the entire data, there is a partition by clause. I have also showed the same thing while learning the ranking function. I mean, we have done the ranking function on top of class. Okay, if you can remember. So each of the class we can partition the data. The same way we can partition the data on top of various region. So suppose we have 8 region, we have partitioned the same 8 region. I mean, partition the entire data set by 8 different thing. So we are mapping each of the regions data to each of HDFS component. Okay, so we have, suppose we have 8 EC2 server working as a data node. So each of the data node will be containing or mapped, that is called map operation. So each of the segregation of data will be mapped and stored to a particular HDFS system. Okay. And after that, when everything has been completed, then reduce. We'll be doing the calculation, maybe some aggregation functions over there. So we are reducing the thing. So suppose I think we are doing the summation operation. Okay. So we can sum between each of the particular clusters over there. When the summation is been completed, we can reduce the thing. Means we have 8 different clusters over there. I mean 8 different EC2. We can have an addition of each of the EC2s over there. When it's completed, we can reduce the thing. Number of EC2 should be reduced. We have now 4. Addition of the 2, then we have having 2 again. So this kind of reducing thing should be there. I think I'm not able. It's not clear to you. So just like we are able to successfully map the thing in particular EC2, then we can add each of the EC2's count. When it's completed, we can across 2 EC2 we can have a count total addition. Okay, this way we can reduce the computing power and have the total summation transferred to the output. Okay, and it should be visible to the user. So this way mapping the thing means map the particular data, I mean distribute the data among the clusters, and then while doing the calculation it will be reducing the thing and give us the output. So this is the concept of map reduce, and we have to check while doing the programming part what we'll be covering tomorrow's session. So that day, that time we will be learning how map reduce should be working, and we need to build program such a way that map reduce should be work over there properly. Okay, and the last topic we are having, yeah, just I mentioned the same thing over here. Mapper transform the data across the computing clusters, and reducers aggregate the data. We'll be having ultimately we'll be having some aggregation operation. And those aggregation operation, if we simply do this thing on top of this big data, billions of records, it should took a large time. Maybe SQL timeout should be there by the softwares. We do not get any result as well. But over here, it should be the performance should be, just like we can tell it's 100 times faster, whatever we are running at earlier. Based on the number of computes power as well, it should be determining, or based on a particular memory size of the data node as well. Memory means the RAM. Okay. So each of the parameter is been useful, but this is very much expensive tool. That's why EMR cluster, the EMR tool I told you yesterday, that is not available as a free tier of AWS. So it's using that technology. Lots of EC2 can be accommodated inside it, but it cannot be a free tier technology. We have to pay for it. So that's why we can assign the number of RAM, the size of the particular RAM for each of the data node. We can assign the number of data nodes based on their numbers, based on the sizes, the performance can be improved. Okay, so it's totally upon us, but we need to check how much efficiency we can go ahead with that thing as well. I mean, using less computers or less price, we can have a greater achievement, or the efficient way you have to use it. That can be done by trial and error as well. Okay, so this is the entire steps. Tomorrow we'll be going to learn. Yeah, nothing for today. I didn't prepare much more slides for today for the architecture one. So tomorrow we'll be having what a particular developer or the big data developer have to do on top of that thing, on top of this architecture. The actually 80% work can be done by this architecture itself for the big data thing I'm telling about. But what to map, what to reduce, the aggregation functions and all needs to be written by the Python code. That is PySpark. We can write the same thing by Scala language. Scala is another scripting language. Okay, just like Python. So we can also write the same thing on top of that, on top of Spark. So that is called Spark by Scala. Okay, we can use R language, R, Java as well. So 4 languages can be handled. I mean, if I'm just working with Spark, so maybe tomorrow I'll be going at only Spark. not everything. Peak, Scoop will not be covering by this session. So we'll be covering only Spark. I mean coding part on top of that thing, maybe PySpark. So we'll be learning that thing tomorrow. Some code snippet should be there, not the hands-on because I do not have the setup for Hadoop into my systems. So that's why I have some code snippets and I mean, I'll try to show you with proper understanding what to do and what not. Okay. So, any doubt for today's session? Anything from your side? Nothing? Okay, then let's connect tomorrow uh, with more details on top of the Hadoop chapters. Okay. Okay, then. Thanks, everyone. Bye bye.